Hey guys, so this is going to be the third video in my series of common computer science problems slash interview questions. This one's going to be the longest common subsequence. I go over four approaches on how to solve the problem where I start with a brute force. I'm going to assume you're pretty comfortable with recursion. If not, let me know and I can make a video covering the basics of it. And this video also assumes that you have some basic knowledge about big O notation and common data structures. Without further ado, here's the video. Hi guys, it's me again. Today we're going to be talking about the longest common subsequence. So the problem is, we're given two sequences of arbitrary lengths, and we want to find the longest common subsequence. So, for example, if sequence 1 is given as A, B, Q, D, K, and M, and sequence 2 is given as Q, B, A, D, K, M, Z, Z, O, the answer will be 4. Because in sequence 1, we see that A, D, K, M appears as a subsequence. And in sequence 2, A, D, K, M is another subsequence. And these two sequences are the longest subsequence in both of them, which is why 4 is the answer. So, given that we know this, is there a way we can solve this problem? So, usually what I like to do is think of the brute force solution and improve upon there. So one possibility is to generate all subsequences of sequence 1 and sequence 2 and find the longest subsequence in both of them. So before we even think about writing the solution, we should think about the time complexity of this. So let me write this down first. Brute force is to generate all subsequences in this. So the brute force is to generate all the subsequences. And what is the time complexity? The time complexity to generate the brute force will be, say, let's say N1 is the length of sequence 1, and N2 is the length of sequence 2. So this approach, what we might be able to do is, say, to generate all possible subsequences, that will be exponential time complexity, because at each letter we can choose either to keep or reject the letter. So this would so the overall time complexity I'm thinking would be O of 2 raised to the n1 plus 2 raised to the n2, something like that. But what does this look like in code? So let's make a class. Let's see as 1. Let's make a class that where we can explore multiple approaches to solving this problem. And approach 1 will be the naive approach. Let's call it a super naive approach. And it takes in two inputs, S1 and S2. Let's call it S1 is sequence 1, S2. Okay, so how do we go about solving this? So like I said, we can generate all possible subsequences. So let's do that. Def gen all generate subs 1. And we need to store the sequences in something that we can look up to compare this. So when we generate these subsequences, and we want to compare whether or not a subsequence in the other sequence exists, we need to store these subsequences in a data structure that allows fast lookup. So let's store it in a hash table. So let's see. To generate the subsequences, this will take 2 to the n time complexity. and space complexity is n, because the recursion depth will be as deep as the length of the string. Okay, so how do we actually do this? Scene dot add without a current string. For I in the range of idx, the name of string. Let's see, it should be s cur plus s of I plus 1, c, and then we want a dictionary to hold subsequences of S1 and S2. So what would the initial state look like? So we want to pass a string. Initially there's nothing, so we pass an empty string. And the first index would be the 0th index. And this is scene 1. And we want to do it the same for scene 2. Okay. So let's actually just test this out to see if we did it correctly. Let's see, print C1, print C2, subsequences in this one. Okay, let's check if this works. Class. Oops. LCS dot 1, and then let's try maybe S1 is equal to ABCD, S2 is equal to DFG, DF, S1 and S2. Ooh, let's see, I made a mistake somewhere. Dic has no operation at. Oh, oops. So I was using a set. Okay, so let's see if the subsequence makes sense. Subsequences in, oops, see if this makes sense. Subsequencing S1, ABC. Let's see, does AD exist? AD exists. Yep, this seems to look correct. Okay, now that we have all the subsequences, it's pretty simple. We just want to find the longest subsequence that exists in both scene 1 and scene 2. So let me write this out. Now we want to find the longest subsequence that exists in both the scene 1 and scene 2. So we might do something like this. For subsequence in scene 1, if subsequencing scene 2, 0, s equals max of is name of subsequence, and maybe so let's check if this is correct actually. So let's go back to our original example, sequence 1, sequence 2. So at the end, if the answer is correct, we are expecting 4. Is it correct? Yep, the answer is 4. Now you can see that this generated all the possible subsequences in S1 and S2. So this is not a very efficient algorithm because this is an exponential time complexity. And so what we want to do is actually think about how to maybe save the results and to see if it's possible to speed our calculation. But first to do that, we need to think about the state of our algorithm, each particular recursion call. So if we take a look at line 26 to 29, that's where we're generating our subsequence. So we're literally just calculating all the or generating all the subsequences. So it's really difficult to actually think about what the particular state is for S1 and S2. So let's actually come up with a cleaner algorithm with the same time complexity as approach 1, but we're able to actually think about the algorithm in terms of what state the particular sequences are. So let's do approach 2. So let's look at our example, S1 and S2. We want to look at each of these strings and consider what happens when we're at a particular index. For instance, if we look at the, say, an arbitrary index, let's say A and Q, one of two things can happen. They are either equal or they're not equal. So if they're not equal, we can choose to either advance the top index or the bottom index. So what I mean by this is that, say we're at index 0 for S1 and S2. They're not equal. So now we need to check B and Q or Q and B, right? So let me write this down. Initially, we're at index 0 for S1 and S2. We check to see if they are equal or not. If equal, we increment their indices by 1. Else, we need to check the possibilities. So in S1 and S2, the first index is A. A at index at I equals 0 for S1 and J equals 0 for S2. They're not equal because A doesn't equal Q. So two things can happen. So now we need to check two things. So we need to check A with the next index, B, and Q with B. So we check A with the next index in the second sequence, and likewise, we check the second index in sequence 1 with the first letter in sequence 2. So we do this at every single step. And again, this will be this will be exponential time. So the running time of this will now actually be 2 to the min of N1 and N2, because we just need to check the length of the we just need to check the length up to the length of the shortest strings. Because we just need to check the length up to the shortest. Right. Yeah. And space complexity is O of min of N1, N2, because that's the depth of the recursive call. So how do we go about doing this? Okay. Let's write a helper function again. Def helper. So this is still 2 to the n. Complexity. So how do we actually think about this problem? So we need a string, of course, but again, we also need the index. The index tells us the state that we're in. So the initial state that we're in is 0, 0. So maybe we can think of something like return helpers S1. So we can start at 0. Or actually, we can start by thinking the problem from the end. So I think both might work. Let's see. So let's try two things. Let's first try if we can start from the beginning, go to the end, and also see if we can start from the end and go to the beginning. So let's try the beginning one first. 0 to 0. Or actually, yeah. Okay, so this is S1 IDX1, S2 IDX2. So we need to think of the base case. The base case is, one base case is if the two strings are out of bounds. So there's nothing to compare. So then their common sequence must be 0. So if IDX1 equal length of S1 or IDX2 equals the length of S2, return 0. So that's a base case. Another case is if they're equal, if S1 of IDX1 is equal to S2 of IDX2, then return 1 plus helper of S1 IDX1 plus 1, S2 IDX2 plus 1. Right, if they're both equal, then we advance the index for both of them. Else, so now if they're not equal, then we need to return max of, so then we need to check two things, helper of S1 IDX1 plus 1. So we advance the first one and keep the second one constant. And we need to check the second one. Now we keep the index of the first one constant, and we move the second one. 2 plus. And we actually need to take the max of these. So it should be max. So let's see if this actually works. I'm curious to try. So yeah, let's see if this works. So print LCS dot approach to -2. Okay, so I have a bug somewhere. Let's see, what is the bug? Type error not appropriate to non-type int. Oh, oops, this should be returned. Yep, so this works. And I think another approach can also be, instead of starting from the beginning, we can actually start at the end. So like so in here, I start from the beginning of each string. And I think you can actually also do this. 2A. So right, this also makes sense. So now we're starting the end of the array, and every time one of the arrays is 0, we can't go any further back, right? So this is basically the same thing as approach to it. So let's see if this works. 0. Whoops. Oh. So now we need to initialize the starting indices to be the end. So that was why I got 0. Yep. Okay, so now it's much more clearly to see what state we're in. So for for this problem, the state that we care about is index 1, index 2. So let me write that out here. The state that we care about is, so these 2 points define all possible states for 2 sequences. And once we know this, we can think about how to use this fact to solve the problem faster. So before moving on, where you're writing this recursive solution and you want to think about whether or not you can improve your time complexity, it's sometimes good to write out the recursive tree. So the recursive tree is just pretty much the function call stack of what the recursion would look like. It's a little bit difficult to write it on a computer, so I'm gonna write it on a piece of paper and then show you guys. Yep. Alright guys, I'm back. So as you can see, it's really hard to talk about this problem without a piece of paper because I'm about to draw an example. So I pretty much just wrote the pseudocode for the longest common subsequence here. So let's just recall. the base case. If one of the indices are at 0, we turn 0. If they match at a particular index, we add 1, and then we increment both of their indexes by 1. Now, the last case is if at a particular index they don't match, then we need to check the two possibilities. So the state of the system can be defined by IDX1 and IDX2. So let's take a look. So example, let's see. We start at LCS. Let's call it, let's make up a number. Let's call it N and M. And if, let's say, they don't equal, then it's M minus 1, M. We need to check these indices. Now again, if for this state they don't match, oh no, my handwriting. No room. So you can already see that this is what a recursive call looks like for just a few states. And you can see that there's a repeating problem. We're solving the same problem twice. So this means that we can actually simplify our, speed up our algorithm by just caching the state. So what I mean by this, we know the state at, if we know the state at this index, right? If we know the state of this index, these two indexes, this is our state. If we know this, then we only have to solve this problem once instead of twice. And this actually simplifies our time complexity drastically. If we look at our overall function right now, the big O running time, if we write the recurrence, is actually T of n is equal to 2 T of n minus 1 plus O of n. And do you guys know why that is? If we, for the first part, 2 times T of n minus 1, we're breaking the problem down by 1 every time, the IDX minus 1 and the IDX minus 1. And we have to do it twice, right? Max of the problem twice. And what about this last part? I'll leave that for you guys to figure it out. But what happens is if we actually are clever and think about how to remember the state that we're in, so that instead of calculating the same problem multiple times, we actually just calculate the problem once. And if we actually calculate the problem once, then the time complexity of this algorithm actually becomes polynomial, specifically n times n, where n is the length of the first sequence and n is the length of the second sequence. So what I'm suggesting is let's actually remember our results in every single state so that when we visit a particular state again, we don't have to calculate it. Okay, let's go back to the computer.
Alright guys, so I just drew out on paper what the recursive call for approach 2 will look like, and how we can actually think about the problem as basically looking at every single state that's defined by index 1 and index 2 of sequence 1 and 2 respectively. And when we look at the recursion tree, we saw that subproblems actually reappear. So instead of just recalculating them every time, we can actually just modify approach 2 to remember our result. So it's like, why calculate something when we have already calculated it? So this is basically a time-space trade-off. So if you think about it, if we have to memorize it, we need to trade space for it. But by trading space, we're improving our time complexity. So let's do that. So let's look at maybe approach 2C. So we're actually almost done. So we're going to reduce this time complexity from exponential to polynomial in time and space. Why time and space? Time, look at the recursive tree and figure out yourself. And space, the hint is that basically we need to remember all the possible subproblems that we're solving, all the distinct subproblems. And actually the trick is that all the possible, all the total number of subproblems is the time complexity. Okay, so now how do we actually remember what we solve? Well, it's simple. We just remember the states. So this is what we can do. Let's call it cache. It's a hash table because we want constant time lookup. So we're trading space for time. So let's say L if x1 id x2 in cache, return cache x1 id x2. So we return it. So if we have seen this state before, we just return it. We don't need to do any more. So what does this look like? This looks like this. And that's it. We just literally added 2 lines. Line 2 was 3 lines. Line 1. Basically it's 3 lines, right? We literally just added 3 lines and we improved our time complexity drastically. So let's actually time it, if you don't believe me. Let's see. So let's test out this new approach. Oh, I made a mistake. Oh, cache is not defined. Oh, yeah. This should be in here. I messed up my scoping. So this is how fast this approach takes. Let's put that right here. Now let's try approach to A. Oh, oops, this should be B. Let's see how fast 2A takes. You can see that 2A takes longer than 2. You can see that basically when we cached it, the results are much faster. I think if I added this much more longer strings, we'll be able to see the time difference more significantly. So I just added literally a bunch of random letters. So let's see how fast our first approach takes. This might take too long. Let's see. So first approach, it's running. It's exponential, so we expect significant increase in time. So yeah, maybe I made the strings too long. Come on. Oh, I'm going to count to 10, and if it doesn't run, I'm going to stop it and just make the strings shorter. 1, 2, 3, 4, 5, 6, 7. Okay, it's taking too long. I'm just going to stop it. So let's actually see if we can finish with approach 2. 1. Okay, you can see that in approach 2, it finished in 0.0004 seconds. Whereas in approach 1, like I counted to like 10 seconds and still wasn't finished. So obviously you can see that by just using a hash table, by trading space, we get significant time improvements. So this is actually called dynamic programming. We're caching our results to solve this problem. So in dynamic programming, there's a bottom-up and top-down approach. And so so far I've used, I think it's a top-down approach or bottom-up. I don't know the exact terminology. But basically, what I have done is identified the states in the recursive approach and cached it. Now, when we're able to do this, we might be able to actually solve this problem iteratively. The iterative solution actually has the same time and space complexity as our recursive approach. So asymptotically speaking, in terms of big O, in time and space, they're the same.
However, in practice, recursion is slow and it's limited by the recursive call stack. So iteratively might be better because for iterative solutions, we're limited by our RAM. But in terms of the big O, they are the same. So let me write this out for you. Def approach 3. Iterative DP approach also has O of 1 times term in time and space. And how do we actually think of the iterative approach? So actually, when I'm solving these problems, I always do the brute force and then the cached solution and then try to come up with an iterative solution. Because if we were able to identify the states clearly, then the iterative solution should come out pretty naturally. So let's take a look at our approach 2B. Okay. In 2B, we see that two things can happen. Two possibilities, basically. First, if the strings are equal, then we add 1 and then move both indexes by 1. So maybe we can think of something like this. At a particular state where I and j, or maybe close index 1 and index 2. So if equal at idx, if equal, right, then we say it's 1 plus LCS of idx1 is 1 and idx2 minus 1. Else, now if they're not equal, then at a particular state, we need to find the maximum, right? This max of LCS idx1 minus 1, idx2, idx2, 1, idx. So actually, this is it. This is all we need to do. We need to so I translated our recursive approach in line 69 to 83 into what the recurrence will look like, and that's given in lines 88 to 91. So actually, we're pretty much down. Now the hard part of this is translating this into code, and I think it'll be much clearer if I were to again write out the example for you guys. So let's go back to the white paper.
Alright guys, so I'm back. So now we're going to be talking about the iterative solution. So I pulled this example off of Wikipedia because I don't have any imagination at all. But basically what we're trying to do is when we're given two sequences, think about how we can remember all of the states. So each state ij represents an index in sequence 1 and sequence 2. And the reason why we want to do this is because this problem has an optimal substructure, meaning that the results in one particular state can be used to help me find the result in another particular state. So you'll notice that I made a table right here. That's basically the length of the first sequence times the length of the second sequence. So these are the total number of states there are, which is why the time and space complexity is the length of the first sequence times the length of the second sequence. Now, let's look at our formula. This is the formula that we were able to figure out by coming up with a recursive approach that uses cache. So basically, if at a state they're equal, we move both index of the string and add 1, right? Add 1 because they're equal. Now, if they're not equal, then we take the max of the two possibilities, the two branches that we go down. Remember our recursion tree? Okay, let's look at our example. So we initialize this table all to be 0 at first, and we actually, if we do an example, let's just do a few iterations. So we start at A, at this state, this box. This box needs a state. We compare this state, A was nothing. That's 0. G was nothing, 0. C was nothing, 0. A was nothing, 0. T was nothing, 0. Right? That makes sense. So now we start down here. we actually can just ignore, yeah, let's just start down here. So if we are starting down here, we can actually just ignore this column because it's comparing just 0 with nothing. If we look at A, right, again, now we compare, let's see, we're comparing A with nothing, right? Sorry, we're comparing A with G. They're not equal. So then we check this box and this box, right? Let's say again, we first compare A with G. They're not equal, so we need to check this box and this box, right? If we look at our formula, that's exactly what it tells us. And what this box means is that we need to check what happens if we include the particular state or exclude this particular state and see what that maximum value is. So again, it's 0. So now we move over one. We check G with G. Is G with G equal? Yes, G with G is equal. So we move this to 1 plus both indices minus 1. So we go diagonal, plus 0. So that's just 1. Now we check C with G, that's 0. A with G, that's 0. T with G, that's 0. Now we check A with A. And what does that give us? That gives us 1. Because 1 plus 0 gives us 1. Now we check G with A. They're different, so we need to take the max of this state and this state. And in this particular case, they're both equal. So it's 1 again. Now we need to check C with A. They're different, so we need to take the max of this state and this state. And that's also 1. And now we're here. So at this state, we check A with A. They're equal. And now we check the diagonal. It's 0, so we add 1. Likewise, A and T, they're not equal, so we take the max of this state and this state. It's 1 again. And pretty much, oh wait, did I make a mistake? Oh wait, I actually made a mistake. Yeah, I made a mistake. Yeah. I made a mistake in this iteration after here because 1 plus 0 makes 1, not 0. So you gotta make sure you know you're adding. 1 plus 1 makes 0 because at this particular state, when we check C with G, they're different. So we need to take the max of this state and this state, and that should be 1. And at this state, we check A with G. They're different, so we take the max of this state and this state, so it's 1. Likewise, at T and G, they're different, so we take the max of this state and this state. That's 1. Okay, now we check A again. They're equal, diagonal 0. Okay. G and A, 1. C and different, 1. A and A, they're the same. Plus this 1, so it's 2. So this should also be 2. And I think you guys get the point. And you should also try to do this for yourself for the last row and see what you get. So now that you kind of have a visual, we did a visual walkthrough for part of our problem, can we actually implement this table in code? Specifically, we want to be able to figure out how to implement this iterative solution based on these two equations that we were able to figure out. So let's go back to the computer.
All right, guys, we're back. So let's try to actually think about how we can put the iterative solution in practice. So basically, we want to translate lines 88 to 91 in an iterative solution. It's actually quite simple once we have the recursive solution figured out. So let's get the length of each string. So n1, n2 go to length of s1, s2. And we need to make a table to hold all to the states. So let's call it LCS, just like I did in the paper. 0 for 0 times, let's see, n1 plus 1 for
2 plus 1. So this will initialize our table holding all zeros. And we do the plus 1 to hold a null marker because we need to consider the base case of what happens if they're not equal, right? If they're not equal, then when we go to line 91, then we take the max of 0 and 0 and 0. If we don't add the 1 in there, we'll get an out of bounds error. So let's solve this for, let's see, I in range of 1 to n2 plus 1 for j in range of, I started at 1 because we don't really need to compare the zeros column and row because they're just 0 by default, because we want to make sure that in line 91 and 89 we don't get an out of bounds error. So if s1 of j is equal to s2 of I, then we look at equation line 89. So that's LCS ij is equal to 1 plus LCS I minus 1, I minus 1, j minus 1, else LCS of j is equal to max of LC I j minus 1 I minus 1 j. Does this match our equation? Yes, it does. And we want to return an answer then. So let's initialize it to 0, and then ants goes to max of ants, and right. We initialize it to 0 because that's the smallest length it can be, and we take the max at each state. So let's take a look into see if approach 3 gives us an answer. Oh, let's see, I made a mistake. Oh, oops. This is not pseudocode anymore. This is real code. Let's see. Okay. What's a house string index out of bounds? Let's see, 0 is n1, so inner loop is j. Outer loop. Where did I make the mistake? Oh, oops. Yeah, right here. Because it's out of bounds right here. Cool. So I think this is actually our solution. Let me just double check to make sure I didn't make any mistake. So actually, oh wait, actually this should be, because we need to iterate for a whole table, and this should just be -1. Yeah. Because remember, we're starting at 1. So we need to compare the first index in our string. That's why I do -1 here, so these can be initialized to 0. Great, so let's check our original example actually. So this should give us, I think, 4, was it? Yep, cool. So you can see this is like 9 to the -5 seconds. Let's see how fast our approach to B takes. Also 9 to -5, because they both have the same asymptotic time complexity. Well, let's try 2A. So this one should be slower. Yeah. Okay, great. So this is a dynamic programming solution, and as usual, guys, you can see that when I'm working out through some of these problems, I make mistakes because I'm human. But like when you're writing out code, always kind of talk out loud or think out loud, because that way you're kind of basically giving yourself mental sanity checks. As you can see, when I was doing the table solution, the iterative solution, I realized I made a mistake when I was checking out each state, and I was able to fix that. And And likewise, when I was trying to debug line 99, I realized I forgot the -1 each of these, the all by 1 error, because I initialized my table to be n1 plus 1 and n2 plus 2, and I wanted to start at the beginning of each string. So that's why I need to do -1 and -1 here. So let me know what you guys think, and I hope this helped out with you guys. Let me know if you guys like these videos where I solve a problem by first giving out like an approach that's brute force, and then think more about the intuition of the problem, come up with a better brute force solution, then a better solution, and then a better solution, and then even better one with examples. Yeah, let me know what you guys think. And basically what I think about when solving this problem is like the number one advice I would have you guys for solving complicated dynamic and programming problems is to like and subscribe to my channel. Alright guys, I'll see you guys next time.